So this is our first topic for slope and deflection of determinate beams. We have the double integration method. First, for the analysis, we're going to consider a simply supported beam loaded with a P force. And it's going to be divided into two parts, one on the left side, L1, and L2 on the right side. And because of this application of the P force, the beam will deflect. As you can see in the broken line, that is the deflection whenever you apply a downward force. And that is a type of a positive bending. So I just have exaggerated the deflection para makita nato that there is a deformity in the displacement or in the position of the beam. With that, the next thing to do after solving for the values of the reaction, we're going to cut the rightmost end of the beam, always at the rightmost, and consider the left section. And by that, redrawing the figure, we have R1 and P force. And since we cut through that point at the right side, we will supply a resisting moment positive bending. And with that, we are going to describe the function of the point of cutting from the leftmost end. And that is an x function. That is the location or the distance from the leftmost end to the right portion of cutting. And of course, the P force will now be expressed in an arm of x minus L1, not L2. As you observe, we establish a function of x. And we are not saying that it's L1 and L2 anymore. And after that, we're going to use the summation of moment, for we are going to get the moment equation. How to get the moment equation? Basically, we just have to get the summation of all moments at the point of cutting. We will consider the clockwise positive and counterclockwise negative. For this, once makuha na nato ang summation of moment at the point of cutting, we are going to now get the integral of the moment equation. And by that, we will get the EI function of the theta or the slope equal to the first integral of the moment equation or moment or m dx plus the C1 or the first arbitrary constant. And we call it the general slope equation. The next thing to do is to further integrate the function. So with that, we will be getting the EI delta, and that is equal to the second integral of the moment equation, or the mx dx, plus the integral of the first arbitrary constant, plus the second arbitrary constant, C2. And this is the general deflection equation. Since we still have the equation form, then our objective is to be able to get the solution for both equations, slope and deflection. With that, we're going to get or evaluate the C1 and C2. How? We have to always remember the supports and its effects to slope and deflection. Whenever we have hinges and rollers or a combination, then always remember that at that point of placing the reaction, delta or deflection is equal to 0 and slope or theta is not equal to 0. Since deflection is equal to 0, then we are allowed to use the general deflection equation. Then substitute the delta equal to 0. Next is if we have a fixed support. Fixed support will give us two values, deflection equal to 0 and slope equal to 0 at the point where the fixed support is. So with that, we can use the simultaneous equations, general deflection equation and the general slope equation. Always remember, for loads not continuous up to the right end of cutting, continuity should be preserved. How do we preserve continuity? For example, if this load 20 kilonewtons per meter is not continuous to the rightmost end, what we're going to do is supply the discontinuity loading. How? We just have to extend the same amount, which is 20 kilonewtons per meter, up to the right end. And since we're adding that amount, we have to subtract the same amount. As you observe, both are of different directions, but of the same intensity. How about for triangular loading? If for a triangular loading is used, then we have to maintain the slopes 30 kilonewton per meter applied in the triangular loading. And with that, you observe rin na to. And since we're adding that same amount, then we are going to get that amount. Subtract rather. And to know the value at the rightmost end, all we have to do is use the proportionality of a triangle. Also, neglect the term or set the term to 0 when the value inside the broken or the pointed bracket is negative after the value of x is substituted. So again, kung mo negative gani ang inside sa point bracket, ang buhaton nato is set to 0 ang term. How? For example, when x is equal to 3, like for example with the expression 35x squared minus 10 pointed bracket x minus 4 to the square or to the 2 plus 5 pointed bracket x minus 2 square. And substituting the value of x equal to 3 this time here, what we're going to get in the next line is 35 pointed bracket cube or the square of 3 minus 10. And remember, 3 minus 4 is negative 1, so do not forget that. And observe the exponential power, square. Then plus 5 times. The 3 minus 2 is positive 1, so that's 1 square. And as you observe in the middle term, the negative 10 times negative 1 square, the value inside the point bracket is negative. Therefore, we have to set that function or term as equal to 0. Finally, the term would now be 35 times 9 plus 5 times x. 5 times 1. The reason why we're going to set the value 0 whenever the value inside the point bracket is negative, because we assume from the first illustration that we have set the value of x as a function from the leftmost point of our beam to the rightmost point of the beam. So from the origin to the right, then all the values of x should be positive. So walay negative sa tanan nga atong execution. So therefore, since that moment arm is negative, then it's irrational. So wala siya ilapot sa term. Kaya ang atong gigamit all the time kay positive values of x. Next, raise to 0 exponent for moment arms of moment or rotational loads. For example, natay moment load, then parisa nato og moment arm kung unsa iyang location, but we have to raise it to the 0 exponents. Because any number raised to a 0 exponent is 1. So 1 times the moment value, it's still the moment value. Let's proceed to our example number 1.